Everything matters in programmable packet scheduling. Packet scheduling has been a classical problem in networking for many years, and it tries to answer a very simple question, which is, out of a set of packets in a buffer, which packet should we send next, and when should we send it? And the interesting part of packet scheduling is that depending on which packet you send next and when you send it, you can achieve different performance objectives. So over the last years, researchers have come up with all sorts of scheduling algorithms trying to optimize for these performance objectives. We have algorithms trying to minimize flow completion times, algorithms trying to minimize tail packet latencies, and algorithms trying to enforce fairness between tenants in the networks. So the obvious question comes to mind, which is how can we deploy all these scheduling algorithms on hardware? A naive way to do it would be to try to go ahead and implement each and every one of those schedulers. But of course, the resources that we have on existing ASICs are limited, and this naive solution will not scale. Another option would be to try to come up with a universal packet scheduler, meaning a scheduling algorithm that could outperform all the others and that could be used as a wildcard in any situation, in any scenario. Well, recent work has shown that a universal packet scheduler does not exist. The final approach will be to try to come up with an abstraction that allowed us to represent scheduling algorithms on top, with the idea that if we could deploy this abstraction on hardware, we could also deploy those algorithms on top of it. And that's exactly what programmable scheduling tries to do. Programmable scheduling allows network operators to flexibly decide the best scheduling algorithms that outperform for their specific requirements, application requirements, and traffic demands. The first thing that we need to make scheduling programmable is an abstraction, meaning this framework that allows us to represent scheduling algorithms on top and that facilitate not only the design of those algorithms, but also the deployment of those algorithms into hardware. PIFO queues have been recently proposed as such an abstraction with the idea that most scheduling algorithms can be decomposed in two parts. A rank computation part that defines a priority, a rank to each packet, defining the priority with which the packet should be sent, and a PIFO queue that pushes packets into arbitrary positions in the queue while only draining packets from the head, so being able to effectively sort packets at line rate based on their ranks. So the rank computation part is the programmable part where the operator defines the priorities with which the packet should be scheduled, and the PIFO queue is fixed that essentially just sorts packets at line rate based on these ranks that we have defined. PIFO queues can be characterized by two key behaviors. An admission behavior, they always admit those packets with the lowest ranks, and a scheduling behavior, they always send first those packets with the lowest ranks. So now that we have the abstraction, of course, the question is how can we deploy those PIFO queues on hardware themselves? One way to do that will be to come up with a new ASIC. We've seen before new ASIC designs or new hardware designs trying to achieve these PIFO queues. Having such a new ASIC, implementing a vanilla PIFO would give us a high level of accuracy. The problem is that coming up with a new ASIC is a costly and lengthy process. So it takes around 5 to 10 years to come up with a new ASIC, and it costs around $200 million. And as proof of that, PIFO queues were proposed in 2015. Now it's 10 years later, and we still don't have a PIFO implementation on vanilla on a switch. Another approach will be to leverage programmable switches to approximate those PIFO queues on hardware. These programmable switches allow us to program new functions on hardware without need for new hardware designs. The advantage is that these programmable switches are around, and we can use them today, and they just cost around $10,000, so much less than, of course, coming up with a new ASIC. The question that we still have is whether we can achieve enough accuracy to make such a PIFO approximation practical today. And that's what we try to answer in this work, and it's not the first time that we do it. So in 2020, we proposed SP-PIFO, which we were already trying to approximate PIFO queues by using programmable switches. And the intuition back then was that it was possible to approximate PIFO queues on programmable switches by using strict priority queues, with the idea that by mapping different packets of different ranks to different priority queues in increasing order of priority, we could achieve an approximation of the PIFO behavior. And if we have a sufficiently large number of priority queues, we can achieve an ideal PIFO behavior. Specifically, if the number of priority queues is bigger or equal than the number of ranks, we could achieve an ideal PIFO scheduling behavior. The problem is that in practice, the number of queues is limited, and it tends to be much smaller than the number of ranks. And when that happens, this means that different ranks need to share the same queues, and we can have cases for inversions, meaning cases in which low-rank packets are scheduled after high-rank packets, which does not happen in an ideal PIFO queue. So we proposed an adaptation strategy that tried to smartly map packets to different priority queues so as to minimize the cases of these inversions happening, meaning so as to approximate the ideal behavior of a PIFO queue. However, SP-PIFO, while it manages to approximate the PIFO's scheduling behavior, it cannot approximate the PIFO's admission behavior because it leaves admission as a byproduct of the scheduler's design. It does not control admission proactively. And the result of that is that non-important packets, packets of high ranks, can leak into the queues and occupy the buffer, not letting important packets, packets of low ranks, getting access to these queues, meaning we end up dropping important traffic because non-important traffic is occupying these queues. The year after we proposed SP-PIFO, IFO was proposed, proving that it's also possible to approximate a PIFO queue by using a single FIFO queue and an admission control defining which packets to be dropped. And the intuition here is that if we can drop those packets with a high rank and just let in those packets with the smallest ranks, we can also achieve a good PIFO behavior, and especially for the case of shallow buffers, where it's more important to decide which packets get in than the order at which we send the packets, this approximation can be quite useful. The problem is that since IFO runs on top of a single FIFO queue, it does not have support for scheduling. We cannot prioritize those packets that are more important. And therefore, we can have non-important traffic being scheduled before important traffic. And that same problem extends to all the works that have been proposed to date. So existing works only approximate one of the two key PIFO behaviors. They either approximate admission or they approximate scheduling. And what we claim here in this work is that both behaviors matter in programmable packet scheduling. So we have to take into account both admission and scheduling if we want to achieve an ideal PIFO behavior. And that's exactly what we try to answer in this work. Can we approximate both PIFO behaviors on existing programmable data planes? And the answer is yes, and that's why we're presenting PAX. So PAX stands for Packet Scheduler, or Programmable Packet Scheduler, and it's the first programmable scheduler that approximates PIFO on both scheduling and admission behaviors. And the intuition is quite simple. If we have a sequence of packets and we are able to know which packets are coming, we could predict in advance what packets we should admit, meaning the lowest possible ranked packets that can fit into the queues, and how to map them optimally to the different priority queues to achieve an ideal PIFO behavior. So we can see here in the slide, in this case, we have a sequence with packets from ranks from 1 to 5, and we can see how if we only admit those packets with ranks lower than 3 and map the packets with rank 1 to the high priority queue and packets with rank 2 to the lower priority queue, we can achieve an ideal PIFO behavior. The question is, of course, how can we achieve this functionality, this behavior, automatically without knowing in advance what packets we will receive? So that's exactly what I'm going to explain next. So we will explain first the admission control and then the queue mapping. So what packets should we admit and how should we map admitted packets to the different priority queues? And we will do it by taking a look at this same sequence. So intuitively, if we know that we have a buffer availability for 4 packets and we know that we have an incoming sequence for 6 packets, we know that what we want to do is to only admit those 4 packets with the lowest possible ranks. So the way to do that is to just monitor the rank distribution of this sequence. In this case, allowing only the packets, the 4 packets with the lowest ranks, ranks 1 and 2, to be admitted into the queues. And the way to do that mathematically is by computing the quantile for the distribution such that computing the rank for which the quantile of the distribution is lower or equal than the fraction of available buffer space that we have in the queues divided by the total buffer space in the system, or by, in this case, by the size of the input sequence. And if we want to decide how to map packets to different priority queues, we can do exactly the same. So intuitively, if we have the size of each of the different priority queues, we can know which packets we can map to each of the queues by computing, again, the quantile of the distribution and comparing it to the fraction of the available space that we have in each of the queues. And that's exactly what we do. So in this case, we compute the quantile for the distribution in this case, comparing it to the 2 slots that we have in the highest priority queue divided by the total size of the buffer space, and we do the same for the second priority queue. And we can see how by doing that, in this case, we end up with the ideal PIFO behavior. Of course, now we've seen how to do it, how to admit packets and how to map them to priority queues for a sequence. But in real life, we have packets that come in a stream basis. So for every packet that arrives, we have to decide whether we want to admit it or not and how to map it to one of the different priority queues. And in order to do that, we have to modify a little bit the admission condition and the queue mapping conditions. So we have to answer these questions. First, how do we monitor the rank distribution? We do it by using a sliding window so that we can keep track of the latest ranks that have arrived, and we can use them as a reference to decide how to map packets and how to admit packets to different queues. Second, how do we adapt to this buffer dynamism, to the fact that we do not always have all the queues empty? Well, we have to measure per packet the queue occupancy for each of the queues so that we can compute these fractions of the availability that we have in the queues compared to the total buffer size, and we do it per packet. So this is one of the key techniques that we have to do to perform the right admission and queue mapping. And finally, how do we account for workload shifts? We've seen that it's common to have traffic burstiness, so we also add a parameter that is this burstiness allowance so that we can relax the admission and the queue mapping procedure so that we cannot be so tight and to account for some traffic burstiness as well. So this is how PAX works in a single slide. Whenever a packet comes, we update a sliding window with the rank of the packet. We compute the quantile for the rank based on the distribution that we have monitored. Simultaneously, we measure the fraction of available space that we have in the queues with respect to the total size, and then we use that to construct this admission and queue mapping condition that we will evaluate for each and every one of the queues. For the admission and queue mapping process, it's very easy. We just scan queues top-down from the highest priority to the lowest priority, and we check for each of the queues whether the admission condition is satisfied. We evaluated PAX both on software and hardware. So on software, we used packet-level simulations on NetBench, and we evaluated the performance in approximating PIFO, but also the sensitivity to the different configurations parameters, like the window size or like the traffic burstiness allowance. We also evaluated the practicality of PAX when running typical schedulers like pfabric or like fair queuing. We evaluated also on hardware on Intel Tofino 2 and evaluated the bandwidth that we obtain under different priority schemes. And we also evaluated it using MetaOpt, a heuristic analyzer, to analyze the performance gaps with respect to IFO and SP-PIFO as well as PIFO, but also to analyze what are the adversarial workloads that make each of these schedulers perform worst. I will just focus on the three key results, which are how PAX is able to reduce the number of packet drops, the number of inversions, and as a result, the number of flow completion times. So this is the result of scheduling a uniform distribution with packet ranks from 0 to 100. We can see in red how FIFO, first in, first out, generates packet drops uniformly across all the different ranks because it's not able to prioritize and it does not apply any admission control. We can see how PIFO, which is the blue line, performs optimally by only dropping those packets at the higher end of the spectrum, those packets with the highest ranks. And we can see how PAX gets the closest in approximating PIFO, not only in the distribution of the packet drops, but also in the total number of drops. So in particularly, PAX reduces packet drops by up to 60% compared to SP-PIFO. PAX also reduces the number of inversions by up to 7 times and even 15 times compared to SP-PIFO and IFO. This is the exact same experiment, but in this case, we are measuring the inversions, meaning these cases in which we schedule packets in the wrong order, so low ranks after high ranks. Again, FIFO and IFO generate inversions across all the spectrum because they cannot prioritize packets. They cannot sort packets because they rely on a single FIFO queue. We see how SP-PIFO generates inversions only in the higher part of the spectrum, but PAX does so much better because it relies on this traffic knowledge and because it relies on a sliding window-based approach, which we can take into account the previous knowledge of the ranks that we've seen. And finally, how does this translate to practical scenarios like pfabric, in which we try to minimize flow completion time? It reduces mean flow completion times for small flows by up to 33% and 2.6 times compared to SP-PIFO and IFO. And you can see it also here in this graph. So this brings me to the end of this talk, in which we've seen how PAX approximates PIFO's admission and scheduling behaviors at line rate on existing devices. We've seen how it adapts to traffic workloads at line rate by using this rank-aware and queue-aware admission and queue mapping strategy. And we've seen how it's able to outperform existing approaches by reducing drops, inversions, and flow completion times.